Okay, this is question 11 from May 2016, paper 2, time zone 2. And it's actually quite a common, that some people, especially at standard level, tackle for their IA. So what people spend 10 hours doing when writing up projects about it, you've got to do in about, 22 marks, 30 minutes or so. No challenge. Right. Find the value of alpha when x is 10. So we're going to find the size of this angle. The easiest way to do that is to find the size of this angle using right angle trigonometry, because you've got a blue triangle here. And find the size of the slightly smaller triangle. And you find this angle. And so that's this triangle. Find the difference between them, and that'll give you alpha. Okay, so let's do that. So the blue triangle is 6 plus 1, 7. This is 10. Trying to find this angle. Opposite is 7, adjacent is 10, so doing tan inverse of 7 over 10, which is 35 degrees. And the green triangle, which is only 5 across and 10 that way. If you do tan inverse of 5 over 10, then you get 26.6 degrees. Which means that alpha, which was the difference between those two, is equal to 8.43 degrees. Okay, so part B. Show that tan alpha is equal to that. Well, tan alpha, we've just shown tan alpha is the difference between two angles. It's tan, just call it A minus B. Where, I'm just going to sketch the diagram out again. Where A is this angle here and B is this angle here. Put the colour code in just to make that super clear. That's A and that's B, and alpha is the one we're trying to find. So 2, 5 and x. We know a relationship for tan A minus B. It can be rewritten as tan A minus tan B all over 1 plus tan A tan B. That's the compound angle formula that's given to you in the formula booklet. And we can rewrite tan A, the red angle, by looking at the red triangle, the opposite and the adjacent. Tan A is equal to 7 over x, and by similar logic, which is that triangle, tan B is 5 over x. So let's just substitute that into the compound angle formula. We get 7 over x minus 5 over x over 1 plus 7 over x times 5 over x. And that's just a case of rearranging that to the equation we were given before. I'm going to get rid of the x squared in the denominator here. I'm going to multiply top and bottom of that big fraction by x squared. And that will give me, well, 7 over x times x squared is 7x minus 5x in the numerator, and in the bottom it will give me x squared plus 7 5s, 35, 2x over x squared plus 35, QED. That's exactly what we were told to find. So in part C, we're going to differentiate tan alpha, sorry. Which just means differentiating 2x over x squared plus 35 using the quotient rule. Use that as u, that's v. U is equal to 2x, u dashed is equal to 2, v is equal to x squared plus 35, v dashed is equal to 2x, I'm supposed to say 35, giving you v du by dx, two lots, so it's 2x squared plus 70 minus u dv by dx minus 4x squared all over v squared, x squared plus 35 squared, and that just collects to be 70 minus 2x squared over x squared plus 35. That's part C, part 1. C, part 2. Hence, find the value when that is equal to 0. Well, when is that equal to 0? Find the value of alpha when that's equal to 0. So, if that's going to be equal to 0, well, that must mean the numerator is equal to 0. Which is going to give us 2x squared is equal to 70, which gives us x squared is equal to 35, which gives us x is equal to root 35. That's the x value. We've been asked for the alpha value. And we know we started off, if we can scroll back actually, with tan alpha equals 2x over x squared plus 35. So, that was from part A. Or part B? Sorry, it was part B. Tan alpha we showed was 2x over x squared plus 35. And if x is root 35, then that's 2 root 35 over 70. So you just do tan inverse of that number. And you get 9.59 degrees. So in part C, we're going to differentiate tan alpha, sorry. Which just means differentiating 2x over x squared plus 35 using the quotient rule. Use that as u, that's v. U is equal to 2x, u dashed is equal to 2, v is equal to x squared plus 35, v dashed is equal to 2x, I'm supposed to say 35, giving you v du by dx, two lots, so it's 2x squared plus 70 minus u dv by dx minus 4x squared all over v squared. X squared plus 35 squared, and that just collects to be 70 minus 2x squared over x squared plus 35. That's part C, part 1. C, part 2. Hence, find the value when that is equal to 0. Well, when is that equal to 0? Find the value of alpha when that's equal to 0. So, if that's going to be equal to 0, well, that must mean the numerator is equal to 0. Which is going to give us 2x squared is equal to 70, which gives us x squared is equal to 35, which gives us x is equal to root 35. That's the x value. We're being asked for the alpha value. And we know we started off, if we can scroll back actually, with tan alpha equals 2x over x squared plus 35. So, that was from part A. Or part B? Sorry, it was part B. Tan alpha we showed was 2x over x squared plus 35. And if x is root 35, then that's 2 root 35 over 70. So just do tan inverse of that number. And you get 9.59 degrees. Okay, C part 3. We haven't used this fact yet, and they haven't told us that for no reason. The maximum for tan alpha gives the maximum for alpha. So what we've done through this process, differentiate tan alpha, set tan alpha equal to 0, is we've found a maximum or a minimum value for tan alpha, and hence found a maximum or a minimum value for alpha. So 9.59 is either a max or a min, or I suppose conceivably could be a stationary point of inflection, especially considering we're thinking about tan. So part 3 is all about deducing that tan alpha is a maximum. So we're going to find the second differential by going back to the first differential. Now this is the calculator paper. So we could just evaluate this expression on the calculator. But I think the way that it's worded suggests that we do need to find an expression for d2 by dx squared. So let's do that first. So we're differentiating 70 minus 2x squared. We've got u is 70 minus 2x squared. V is equal to x squared plus 35 squared. Du by dx is equal to minus 4x. dv by dx is equal to 2 times 2x times x squared plus 35 to the 1. So sticking that into the quotient rule gives us v du by dx. So this is d2 by dx squared of tan alpha is equal to v du by dx minus 4x times x squared plus 35 squared minus u dv by dx 4x x squared plus 35 times 70 minus 2x squared all over v squared. X squared plus 35 to the 4. At this point, I just want to evaluate that at the value of alpha or x that I've got. And we had x equals root 35. So, well, let's see. I'm probably not going to evaluate it. I'm probably going to just make sweeping statements about the sign of everything. This, in the denominator, is positive. This is positive, and then it gets times by a negative, so that's negative. This is positive. 70 minus 2 times root 35. Actually, that's 0, this bit. 70 minus 2 lots of 70, so this bit is gone. Negative over positive is negative, which means that it's less than, which means that d2 by dx squared of tan alpha is less than 0, which tells us that it is a maximum. And so, not only does it never exceed 10, alpha is always less than or equal to 9.59 degrees. Okay, find the set of values of x for which alpha is greater than or equal to 7 degrees. And we had this relationship, tan alpha is equal to 2x over 35 minus x squared. So this part D, doesn't actually have that much to do with all the other parts. You can sort of answer this independently. It's just calculator skills. The way I'm going to do this is I'm going to plot the graph of this, and I'm going to plot the graph of tan 7. And if tan alpha is bigger than tan 7, that implies that alpha is bigger than 7 on the range that we're looking for. So that's what it looks like once you plot that into your graph, and you can see that in order for tan x, which has come out in purple, tan alpha, sorry, for this to be bigger than this, it needs to be true that x is between 2.55 and 13.7.